Hey everyone, welcome to How Kotlin Powers Functional Design MCP Edition. My name is David Denton. I'm a software consultant from London, and I am co-steward of the HTTP ecosystem, should we call it. For anyone who doesn't know what HTTP is, it's a web toolkit written in pure Kotlin that attempts to model HTTP as just simple functions. So this talk is about how we took the patterns that we learned while modeling HTTP as a function, and then extended it to use to model MCP in its entirety. And we're going to see how Kotlin allowed us to do that and the kind of tools it gives us. So firstly, what do I mean when I say functional design? So what I don't mean is functional programming. So I'm not going to talk to you about monads or applicative functors. What I'm primarily talking about is designing programs using functions as a first-class citizen and using operations on those functions. And this kind of leads to a particular style of design, which is a bit like in England we have this thing called Marmite. Some people love it, some people hate it. You'll make your mind up, but you may feel one way or the other at the end of this. So we do, however, get quite a lot of stuff from functional programming. We get things like immutability, we get pure functions, the simplicity that comes with testing for those functions. But mostly what we're doing is we're programming to expose abstractions into our programming namespace instead of class identity. So if we have a look at what that means, on the screen is two implementations of a predicate. A predicate obviously is an object that takes, it does a test on a particular object, and then it returns a Boolean result. So we've got two implementations. One is a class, that's called isSubstringOf. And the second style is using a function. Now, the difference between these two is that the first instance actually exposes the isSubstringOf type name or class identity into our programming namespace. And that increases the amount of kind of context that we have. The second option exposes only the predicate interface. So we have no kind of class that we know about. It's just the predicate function. HTTP heavily leans towards the second style of programming whenever possible. So how does Kotlin help us? Kotlin gives us quite a few kind of functional weapons in its toolkit. Hopefully, there's 8 things on the screen. I think there are 8, yeah. I'm not going to go through them all, but hopefully you're familiar with at least some of them. You're going to see a lot of them in the code I'm just about to show you over the next 40 minutes. So why Kotlin? Well, Kotlin's design is very thoughtful and tasteful, I suppose you'd call it, as opposed to, say, Java, which does have functional concepts built into it, into collections and so, into optional. But unfortunately, they've kind of been done, in our opinion, in a kind of clunky way. And Kotlin gives us a kind of nice, concise, beautiful language to express our designs in. So let's talk about HTTP, the patterns behind HTTP, the core. Primarily, there are 2 functions that HTTP is modeled with. This is all stolen from Twitter's Server as a Function paper from 2013, I think. And the main one is called an HTTP handler. And that is just a function that returns, it takes a request and returns a response. So it's not even an interface, it's just a type alias. And we can define one of those in line, completely anonymously, like this echo function you can see on the page. We just define a lambda that takes the body out of a request and returns it to the response. So the HTTP handler interface, or not interface, the type is exposed. Now, the second type of function that we expose is called a filter. So a filter is called middleware in other languages, but on the JVM, for some reason, the term filter stuck. You can find it in the servlet library, for example. And what that is, a filter is a higher level, a higher order function that's a function that takes a function as a parameter and returns another function. And what this allows us to do is actually manipulate both the request and response. The filters form a chain through which the request and response kind of flow, all the way to the bit that does the business logic at the other end, which is the HTTP handler. You can see that we are defining an anonymous filter here, which is called reverse. And what that's going to do is it's going to do a request, it's going to get a response, and it's going to take the body string and just reverse it. And note that we are doing this. There is no reverse class, once again. We're just exposing a filter. And we can take these two types of function and compose them together using an extension function called then. You can take a filter and compose it with a filter to make another filter that combines both of those behaviors. And you can also compose any filter with a handler to expose a handler. So what we're getting is like a stack of behavior that can be reapplied, and it's all functional, so it's, it can be applied again and again. And it exposes an HTTP handler. That HTTP handler can be extended or converted into a server using the asServer function, which is an extension function on the HTTP handler type. Started up with Jetty or another one, server engine, and then started. So into this code that we've just created, we're only exposing the filter, the HTTP handler, and the server, and they're all abstractions. But it's no good just replying to every single HTTP message in the same way. So we might have many endpoints that we want to serve. And we can do that by effectively deforming a specification or a description of the service, which creates a predicate on the request that's coming in. So effectively what happens is that you would say, can this handler satisfy this request? And in the case of echo, we've got a path of echo and a verb of post, and we bind those two things together using an infix function. That creates the specification for the route, and then we bind that to the echo handler. This thing itself is also an HTTP handler. We can do the same thing with the delete, and then so we've got two HTTP handlers, and then we can compose those routes together using the route top-level function to expose another HTTP handler that actually gives us routing, so we can take requests, find out which one actually will satisfy the request coming in, which handler will satisfy it, and then dispatch to that one, and then return the response. And we can do this because it's just a function. So so HTTP is 9 years old, 9 years old in a week, actually. And over those 9 years, it's kind of grown quite big. From a tiny 40-line Hackday script written by two guys called Ivan on a Friday afternoon, and now it's kind of it's got a bit of a monstrous kind of presence, I suppose, which we'll see in a sec. But we came across a few rules that we technically wanted to kind of use again and again, and we identified these as being the rules to code by, the HTTP ethos, as it were. The first rule is that we would identify and reuse simple abstractions. Preferably, those abstractions would be just a function. They can't always be functions, but a lot of the time they are. We would compose functions or abstractions together to form other abstractions that we could layer functionality across. And then we could lean on the Kotlin type system and the feature set in order to actually achieve what we wanted. And it turns out that these three rules themselves, when we apply them again and again and again, turn into something actually what we think is quite special. So we identified several different types of module as we kind of went up through the different versions of HTTP. And some of them were HTTP servers. And now the HTTP server base type or base abstraction is called a server config. We saw one of those already. That was called Jetty. That Jetty construction was also not a class. That was just a function call, a top-level function call. HTTP clients in HTTP are just handlers, exactly the same as the server side. And that's actually one of the things that gives the server as a function model a lot of power. And if you want to find out more about that, you can come. We've been to Kotlin Conf a couple of times. There are other talks specifically about that. A template handler is just effectively a thing that takes a function that takes a view model and turns it into a string. And a serverless function, of which we support, I think, 6 different platforms, is a function that takes a context and returns like an adapter that then gets converted into an HTTP handler. So all of these module types, of which they kind of form into sets, and other people on the internet would create them, and so we end up having this kind of sprawling tree of modules. Sorry. And over the last 9 years, we have moved from having 9 modules to having just today over 200 modules. That's been a pretty standard kind of uptick. It's been pretty constant. Some of the modules are us. Some of those modules are other people. But they form kind of 4 distinct ecosystems, I suppose you'd call them, sub-ecosystems, which kind of are broadly kind of grouped based on their functional type, basically. But the really interesting thing is the actual graph on the left, which actually displays a distribution graph of the number of production lines of code in each of those modules. So rather pleasingly, and I was actually very happy when I saw this graph, most of the modules are actually between 50 lines of code and, say, 300 lines of code. And that actually told us, actually, that we had actually hit on some decent abstractions that actually could be re-implemented simply. I mean, at the top end, you've got a couple of really big ones. The core module is a couple of thousand lines. It's still under 1 meg of code in a jar file. There's a balance. We could split it down more. There's a balance between kind of modularity and convenience. And right at the other end, we have things like our Spring Boot bridge, which allows you to plug in an HTTP handler to a Spring Boot controller. And that's 80 lines of code. And it does, I think, it does HTTP and service events and WebSockets. So you can get quite a lot of functionality with a lot of code if you find the right abstraction. And over the years, we found what we thought was kind of a recipe for protocol design. We started with HTTP, we then did WebSockets, and we eventually did service events. Those were the 3 base protocols that we supported before MCP came along. And effectively, we came up with a recipe. So we would define a handler type, a protocol handler type that took a request and returned a type of response. We would have a specification that would actually tell or describe a particular kind of service. And that was effectively it's got metadata, and it's also got effectively a predicate that says, does this request be serviced by the thing I'm bound to? That's a specification or a spec. We can take a handler and a specification, and we can actually bind them together to make what we call a capability. A capability in the HTTP sense is just an endpoint. And then we can compose several capabilities together to form other capabilities that had routing inside them. And finally, we could take a capability, one or many, it doesn't matter, attach it to a runtime, and turn it into a server. And we see this, the thing is, we'll see again and again that the same kind of patterns appear across all these things. So if we look at what that looks like for HTTP service and events and WebSockets, this is the DSL that we did iterate towards. This wasn't the way it was originally, but we managed to pull out the abstraction and remodel everything using the same kind of routing mechanism, which was very pleasing, very, very satisfying piece of work. And then we can take all those 3 capabilities and actually then combine them using the poly, which is a top-level function, and that will combine those different protocols into a single handler that then you can turn into a web server and then start. And so it's exactly the same type of kind of behavior based regardless of which protocol you're using. And you can do the same thing with SSE and WebSocket. You can just turn them into handlers and start them up. And then came Model Context Protocol. In late 2024, Anthropic released MCP onto the world. And it was defined as an open protocol that enables seamless integration between LLM applications and external data sources and tools. If you want less of a word salad, it's USB for LLMs. And so MCP broadly does 3 things. It provides this kind of universal interface. That's the USB analogy. It provides a standard transport mechanism or kind of a message format, which is JSON RPC. And it also provides a set of capabilities which the server kind of gives to the client. So the question for us was, could we apply the recipe again? Could we make MCP usable by just actually defining a function? Now, we had, at that point in November 2024, we had a HTTP AI. It had about 10 modules in. The actual first module we created in that was an adapter for OpenAI's connector interface. That was 2023. So we'd been a year and a half, and we'd done various bits and pieces. But we knew that the MCP was probably going to be something special, and so we definitely wanted to actually support it. And so the question was, could we pull off the same trick again and actually really get down to it, really simplicity. And the TLDR is yes. So what you've got on the screen is a fully compliant MCP server in 2 lines of code, if you don't count the type alias at the top. If we go through it, you've got a tool handler, which is an MCP tool. That takes a tool request and returns a tool response, exactly the same as HTTP. We have a tool specification, which in this case it just says clock and a clock. That's not very descriptive, but it doesn't really need to do anything else. That is our specification, and that is what gets advertised to the LLM as the tool definition. We take that specification and we can bind it to a handler, which does the actual business logic work we do, and that binding creates a capability, and that capability is a tool capability, and we can take that tool capability, we can turn it into a server, and we can start it up. And that's an MCP server. Once again, we're only exposing here tool capability and HTTP server. But MCP is more than just tools. So I guarantee that if you've been to other MCP talks, you've probably seen pretty much 99% of them only talk about tools. Tools is the thing that sucks all the oxygen out of the room. But MCP is more than just tools. MCP is actually, as per the HTTP definition, 9 different capability types, of which tools are just one. Now, we're not going to talk about all of them, but we're going to see how we model one of them or a couple of them. The interesting thing here is that 3 of those capabilities, tasks, elicitations, and sampling, are actually initiated on the server, and the request is sent to the client. The client then responds. So this means that MCP itself is bidirectional, which forms throws a particular set of complexity our way because it's not as simple as HTTP. And there are also more layers. So we have our MCP capabilities at the top, tools, resources, whatever, and we have transport. And the transport in MCP land in this specification is swappable. So we have the HTTP streaming protocol, which is the most recent one. We have server-sent events, which was the legacy one. We've got standard I/O, which is one that actually you can plug it in on the command line. And HTTP also supports WebSockets as well. But in between those 2 layers, there are other layers we need to consider. So for a start, the wire format. The HTTP interface, you send it JSON, and what you actually get back is server-sent events. You get JSON blobs inside a server-sent event stream. So it's not just an application JSON stream. So that's complexity. We also have negotiation. MCP is currently a session-bound protocol, which means there is initiation ceremony, I suppose, a trading of exchange when we set up an MCP connection in the first place. There's also security consider, something that has been rather interesting in MCP land, I'm sure you will probably know. And MCP is settled on OAuth for that. And finally, we have JSON RPC. And as I said, we have, although everything is a JSON RPC message, we have JSON RPC requests, and we also have JSON RPC results from requests that the server has made to the client. So that's before we get to the MCP capability itself. So that's much more complicated than simple HTTP. So in practice, what does that look like? In practice, that looks like you've got a tool handler at the top. If we look at the version of the code, the tool that I just showed you, and there's a server runtime. So those are the basic 2 layers that you need. But in between that, there is an HTTP handler. Traditionally, that lives on post/MCP. That is responsible for taking the HTTP message, taking the JSON out of it, processing the message, and then turning all the stream of responses back into the stream that actually goes back to the client. There's also a protocol. So the protocol layer is responsible for negotiating the session with the client. That means, is this client allowed to talk? It means to this, what is the client allowed to see? That kind of negotiation. And also it says, what version of the protocol are you talking? And also, what are the capabilities that you actually expose? And we'll see what that looks like in a moment. And there's also security as well. And finally, there's the MCP handler. We've got JSON RPC call routing effectively. That's what that does. It determines where this message should end up in your MCP stack. Now, there are 5 layers. Once again, it's more complicated than HTTP by a long way. But actually, what we notice is 3 of those layers are actually following the same mechanic as we did for HTTP. We have a handler, which is a protocol request and response, and we can also have filters as well. So actually, that helps us because we've managed to model these 3 distinct layers as this simple function type. Then actually, that kind of gives us a lot of stuff in terms of like testability and simplicity, and actually the ability for humans and LLMs to understand what's going on. So that was complicated. But luckily, we did have all the bits. Because HTTP at the point of MCP creation had about, I think, probably 180 modules or so. We had all the component bits that we needed to actually create. So we had server-sent events. We had support for that. We had JSON RPC library. We had OAuth security. We had runtimes. We had JSON stuff. So we had all the bits, which means we could just reuse those small modules that we created over the previous 7 years, and just reuse those bits, bring them in, and then the only thing we would have to do would be to actually model MCP itself, which turns out to also be, not so trivial in the first place. So if we look at a more realistic tool, this is the tool that we're going to be kind of looking at for the rest of the presentation. We've got a function, which is get countdown. So this tool provides a countdown to an event. You provide it with a date and a name, and it tells you how long it is between from now until that date, based on a clock. I mean, it's pretty trivial, but it will get the job done. So we can see that the actual tool itself has got like a name, and it's got a description, and it also defines the input and output contract. Now, the input and output contract, the date, event name, and output, are actually defined in the first 3 layers as functional lenses. Now, in HTTP, in the core, there's a lens library. If you don't know what a lens library is, it's basically a lens is a thing that actually is a function. It's actually 2 functions where you apply it to a target, and it pulls something out of it in a type-safe way. And you can see we're doing that with event name and target date. We can actually get out the correct types. We've reused a lot of the lens library from the core, so that's good as well. It's just all function composition. Lenses themselves could actually probably be a 2-hour presentation, so we won't go through it. You just need to know it's a function. And then we've got our tool, we spec, we bind it to our handler, we take the dates out, we calculate how long it is, we turn it into an object called countdown that's got a couple of fields in it. That gets turned into JSON by the output lens, and it goes back to the client. And it exposes a tool capability again. So you see there is no countdown class at all. Oh. And server capabilities, of which a tool capability is one, compose. So we've got tool capabilities here, and we've got resource, prompt, and completion capabilities. I'm not going to go through the rest because they're broadly similar to what you've already seen. But they're all server capabilities as the super kind of interface. And we can compose them together using a capabilities method, top-level function, which will actually compose them all together, provide routing, and actually gives us a server capability back. That server capability can be converted via an extension function into a server and start it up. So let's see what that looks like on the wire. So what we're going to do is we're going to see how to test capabilities, and then we're also going to have a look at the actual what's going over the wire, so you can see. So is that big enough? Hopefully. So this is just a simple unit test. The unit test is defining a clock here. We've got our tool capability, which we create by calling our function. And then we've got the test, and what we're doing is we're measuring how many days between the 1st of January and Christmas on this year. So first of all, we create our request by injecting. This with method is an extension function that is also a high-level function because it actually injects into the request the typed arguments. And then we can call the tool with the request because it's just a function and get out a tool response. And then we can do an assertion on the thing that comes out. So you can see that passes. Great. OK, so that's OK. That's fine. But we want to actually see what goes over the wire. So if we want to see what goes over the wire, we can use this test here, and what we're actually going to use is an MCP client. So the MCP client for this is injected here, and we'll talk about the injection in a second. The MCP client it needs to be started because it needs to do that protocol negotiation. And then broadly, we're creating a request using the same mechanism as we did before. Then we kind of call the MCP client tools API to actually call the tool, get the response, and then actually just do some assertions on the response. So I'm going to run this in a sec, but actually the interesting thing here is this intercept JUnit plugin. So intercept is a part of the Wiretap module of HTTP, which actually we're releasing today. And that allows us to inspect what happens on the wire of any HTTP project, not just MCP. You can do HTTP, SSE, all that kind of stuff. And what you're doing effectively is creating your capability here. You're calling the MCP capabilities method, and that is what causes this MCP client to be injected. So because it actually just connects. Now, you don't have to use this. You can just use a test MCP client, and that's fine as well. It works. But this is a bit more interesting. So if we run that, oh dear, it failed. And the reason it failed, if we look, is because we were expecting 141 days between January the 1st, and it wasn't 141. It was actually only 140. Oh dear. So the test has failed. But what Intercept has done for us is actually create this HTML report. And the HTML report effectively captures the open telemetry traces and the HTTP traffic going between the plugin and the code, and actually displays them on the screen in an HTML report. There's also a Markdown report that I can just press a button and see, but it actually displays it creates all of the open telemetry traces. You can see here we had the initialize call. That's the MCP call that was setting up the connection. That's actually connected by a link to the trace below, which is the HTTP call. Now, in MCP, in the spec anyway, in the OPTEL spec, HTTP and MCP calls are not a child-parent relationship. They are actually linked to each other. So that's why we do the tool call, the initialize, and then we do the post. And then finally, we do the call countdown. And you can see that it's actually given us the inputs and the outputs of what went in, and it's presumably got the session ID as well. So that's what happened, but what actually went over the wire? Well, if we go over here, we can see the traffic, and this is the traffic that actually occurred on the wire. We made 2 HTTP requests. The first one was the initialization call. We set the protocol version. This is the initialized request, which basically says who you are, what you can do, and what protocol version you're talking. That's the negotiation part. And this is a JSON RPC message. They're primarily driven by this method parameter. And the response, what's happened is that the server has dished out a random session ID, and it's also then, you can see it's returned event stream. This is the SSE event stream with a message, and this is the data. And so this list can have obviously more than one thing in it, depending on the actual call that you're making. So that's the initialize call, but then we also made the tool call. So this is the second request that happened. We've got the session ID here, which was the one that was just dished out. And then we've got the tool call method with the parameters, and this is the response that we got back, and you can see the number of days was incorrect there. So that's nice because you can actually see what went over the wire. You can kind of see what actually happened. We also provide this report as Markdown, which allows you to actually take these reports, put them into an LLM, and form a contextual knowledge base of how your application behaves, which is all convenient. So let's go back to the slides. So now we've got capabilities. What we can do is we want to complete our server and actually turn that into a server. Now, the code that I showed you before, which was just a capability and starting as a server, was a little bit of a cheat because there are more things that actually are required for a proper MCP server. And those are, firstly, an identity. The server needs to say who you are as a part of the actual initialization part. Then there's security. You can plug any HTTP security mechanism in. Here we've got OAuth security. They're just out the box. You can use bearer token or whatever it is you like. And then we've got capabilities. Now here we're going to, we've got the get countdown tool that we had, and I think that's a resource, and this one is a prompt. That is a capabilities when we compose them together. And then when we do is, what we can do, actually do this guy, is actually to create an MCP app by passing in the identity, the security, and the capabilities. And we're also going to pass in a filter, which is the MCP filter that's going to activate at that MCP layer to actually capture the open telemetry tracing. Once we've got the app, we can turn it into a server, start it up, exactly the same as we had before. And, yeah, so the other thing is that we obviously said at the start that actually what you can do is you can swap out transports. So you can see what I just did there was actually just change the wrapping function from MCP to MCP WebSocket, and automatically the actual thing is talking MCP WebSocket instead of in the HTTP version. So we've just got that swappable layer that's just that wrapping interface. So that's it for kind of core MCP, but there's more. So MCP defines extension points, and one of the most exciting extension points that I think is here is MCP apps. Show of hands, has anyone used an MCP app? No. Good, OK. So an MCP app is effectively a user interface that will live inside like Claude or Codex or any other chat client. What effectively you get is an iframe. We can see with the app, that's where it would appear. And what it does is it allows you to feed context into your MCP server by using a user interface instead of typing into it. That is exposed in MCP by an MCP resource, which is another one of these capabilities. And so what actually happens is that the Claude will actually, it calls a tool to get the name of the resource, then calls the resource. That resource returns the HTML that's then put into the iframe. Now, if we want to actually interact between our application, MCP app, and our server, MCP server, we're actually going to use MCP tools to do that. And what happens there is that the application itself sends a message to the iframe sends a message to Claude wraps that up in an MCP call and calls into the MCP server, and then does the reverse and actually puts the actual values back into the application. So we can see together that an MCP app is just an MCP resource that's been composed with a bunch of MCP tools. It's just using the same composition, or at least in HTTP, that's what it is. And we're effectively defining the extension just by using the primitives that are already in the protocol. Let's see how we create an MCP app. So we've got a countdown app. I'm going to make this slightly spicier by putting an HTTP handler. But effectively, what we're going to do is call render MCP app, passing in some metadata, the list of resources, and the resource meta, which is the content security policy. You see that MCP app resource meta. It's not very pretty, but it's providing the security layer around what the iframe is and isn't allowed to talk to. And you can see at the bottom, there's just the content of the HTML. Now, normally what that would be the result of a template renderer. But we've just put in a string here for this is actually real code, but it's just we're using a string version here. Under the covers, that MCP method isn't doing, that render MCP app method isn't doing anything clever. All it's doing is effectively calling that capabilities method, composing together different MCP capabilities. And that returns a server capability that can once again be returned into a server and started in exactly the same way as we've seen about 7 times by now. So let's see what that looks like. So what I'm not going to do is I'm not going to demonstrate using Claude, because I'm not stupid enough to attempt a live demo on the internet with an LLM. So what we're actually going to use is Wiretap. So Wiretap, the other part of Wiretap that isn't Intercept, is a developer console that kind of forms a transparent proxy around your application, and it allows you to capture the traffic going in and out of the application and to play with the MCP tools, and we'll see what that looks like. So if we go and look here, this is our application. Hopefully you can see that. We're basically doing exactly the same thing here as we were doing on the other slide. We've got an identity,
we've got our HTTP client, we've got some capabilities, and we're composing all those things together. We're going to add an extension of MCP apps. So this is the protocol. When the Claude makes the connection, for example, it's going to say, hey, I can do MCP apps as well. And we're also going to do some open telemetry tracing at 3 different points. We're going to trace the inbound calls, which you can see this one here. We're going to trace the outbound calls, which is here. And we're also going to trace the MCP calls as well, 3 different points. Now, this HTTP client is used for the other tool that goes into the Countdown app. So if I click through to the Countdown app, you can see that actually we're calling this getRandomEvent tool, which is going to load information for events randomly into our application. So it's just another tool that we're going to call. If we want to run the MCP app inside Wiretap, as I said, Wiretap basically is an invisible proxy around your application, and it also kind of sits and provides a user interface. It also provides an MCP server itself, so that you can plug the Wiretap MCP into, say, Claude or Codex, and actually the LLM can actually interact with your application by firing traffic at it through the Wiretap interface. We're defining a local target, which is here, which is a poly, because it's a poly handler, and it has got this is the demo. So if we start this up on 1, 2, 3, 4, 5, you can see it started up, and it's actually started at _Wiretap. So that's the user interface. The actual main application is still running at the root, and what's happening is that Wiretap, well, it's an invisible proxy, it will just take requests and forward it to the underlying app. So you can still test through the normal interface, but you get this Wiretap user interface on the top as well. So if we click on that, we can see what it's got. So this is the user interface, so just click up. So the Wiretap interface, this is like the home page is like what's going on inside my JVM. You can see the number of classes loaded, how long it's been up, the memory usage. It's got the state of the MCP server and a couple of statistics about the HTTP traffic that it has already recorded. If we go over to the MCP tab over here, and if anyone has actually used that's probably a little small. There we go. If anyone's used the MCP inspector, which is a node application. This is broadly the same thing, just written in pure Kotlin. It allows us to interact with our tools that we've defined. So there are 3 tools here. So there's the countdown, the random event, and the show UI. There's the resources. This is, if we look at this resource, we can read the resource. And this is the content of the HTML that we'll call. And we can also, if we flick over to the apps tab here, if I don't do that badly, we can see this is the application that was defined by that HTML. So we've got a couple of things here. We can load a random event. That's going to call out to that third-party server. So the world's biggest kickabout returns. Global sun goes dark for a bit. These are all inspired or created by Claude. I'm not sure if they're real things. And once we've loaded that random event into our UI, then we can say, how long is that? And it will tell us the count days. So we've got our different tool calls that are going either through the server or the get countdown tool. It has recorded the open telemetry traces, of course, in exactly the same way as the Wiretap intercept plugin did. You can see that we've got all the open telemetry traces for the tool call HTTP and the outgoing call. And it also forms a interaction diagram. We've got things like timing, critical path, that kind of thing. And we can also see, if we call all the various types. And the traffic, once again, is also recorded in exactly the same way. So all this is kind of like giving you a nice little kind of developer console that you can actually use to test your application. There's also chaos functionality built in. So what it means is you can actually say, well, when you get this particular type of call, I want you to blow up with a 405 or a 502. Right, so that is it for Wiretap. So, as I said, these are the 2 things you've seen. There's MCP, MCP function, module, and also Wiretap, which has gone into production kind of today, so you can get it to download.
have a play with them. Hopefully, they're kind of useful to people. And we're seeing people seem to really like, especially the open telemetry tracing capture is particularly popular. So what did we learn over the last 9 years? So HTTP we learned that functional design is domain agnostic. So if you iterate enough and you find the right abstractions, you can actually use the same abstractions across different protocols. You can see, remember, we had our MCP kind of solution, and that actually had 5 levels, but we actually managed to use the same mechanic across 3 of those levels, and actually that reduces the amount of kind of stuff that's coming into the context, and hopefully it's simpler for everyone. Small abstractions are definitely easy to compose, so try to minimize, aggressively minimize what your abstractions do. Reuse over rebuilding. When we came to implement MCP, we noticed that actually what we had was we had to do server-side events, and we had to do security and all those other things. But we already had all those parts, which were actually nicely kind of contained, and we could just draw them in, leaving us with the very trivial task of just implementing MCP. Simplicity, we think, is strategic. It's better for humans to learn. It's better for LLMs to learn. Simple code with no magic is more secure. Simple code with no magic is simpler. There's no place for bugs to hide. And it's going to be interesting because as of this week, the MCP draft spec, which I've read, which is they're going to make MCP fully stateless. In the next version, I think, which is going to be interesting because all the SDKs are going to have to basically be re-implemented. But hopefully, our layered approach will allow us to actually just switch out that protocol layer when we move from a session-based to a non-session-based model. The damage, I suppose you call it, is going to be contained in just that layer. And finally, Kotlin we found over 9 years and 200 modules and 1,000 releases that Kotlin is perfect for this kind of design. It allows us to elegantly express designs and compose programs together. We're very, very happy that we've got Kotlin. It's great. We can't imagine having done the same thing in Java. It would have probably been a nightmare. But that is all we've got time for today. So that is the end. Thank you very much for listening.